We're now going to talk about an interesting process called semiconductor doping. And this is a process that is very important, as you'll learn in the next lecture, for modern electronics and technological developments. Now, to understand what semiconductor doping is, let's briefly talk about what sort of semiconductors exist. Now, we're just going to be considering pure elemental semiconductors. And this is things like silicon and germanium. Now, let's just focus on silicon for the sake of this video. Now, the first thing to note is how silicon forms bonds in the crystal structure of the semiconductor. So, silicon is a group 14 element, as is germanium. And what this means is that it has 4 valence electrons. So, it has various electrons below this in lower energy levels, but the outermost energy level electrons are the ones that can interact with the electrons of other atoms, and this is what allows bonds to be formed. So the silicon has 4 valence electrons, and in its crystal lattice, it will share those electrons with the surrounding silicon atoms, and because it has 4 electrons to share, it will form bonds with 4 silicon atoms. So you end up with a crystal structure that looks something like this, and that repeats off into space in all directions, each silicon bonded to 4 other silicons. Now, semiconductor doping is essentially a matter of replacing one of those silicons in the lattice with a different element. This was usually in a very, very small proportion, so a few silicon atoms will be replaced with a different element. And this element, depending which one it is, will have some interesting electrical effects on the semiconductor. Now, there are really 2 groups of elements that we use for doping, at least at this level, what we're discussing, pure elemental semiconductor doping. And those are the group 13 elements and the group 15 elements. And you can find these on the periodic table. They will be the columns just to the left and the right of the column that contains silicon. Now, what effect do these have on the semiconductor? Well, we noticed with group 14 elements, they have 4 valence electrons. Well, group 13 elements have 3 valence electrons. And group 15 elements have 5 valence electrons. So they have 3 electrons to interact with other atoms, and these have 5 electrons in their outermost energy level to interact with other atoms. Now, the effect of this, when we introduced one of these to the lattice, is interesting. So let's draw out. We have 4 silicons here. So this is representing the semiconductor lattice. And we are going to introduce a group 13 element first. Now, group 13 contains elements such as, for instance, boron or aluminium. And these have 1 fewer valence electron. So, the effect of that is that it's able to share 3 electrons. It has 3 electrons in its valence shell. So 3 of these silicons will be nicely bonded. And then it's 1 electron short. So you'll notice, compared to the regular semiconductor lattice, there's 1 missing electron, which we call a hole. There should be one here and there's not. So this is a localized region of positive charge. Now, the effect of this is essentially these holes can carry current as well. And so you end up with the ability for the semiconductor to be more conductive, because it has these holes which can themselves carry current in addition to the electrons. And if you look at the energy level associated with these holes, it's actually within the band gap. So the energy required to get them moving, so to speak, is lower than the energy required for a pure semiconductor. So conductivity goes up. So this results in what we call a p-type semiconductor. P because of the positive hole. Now, what happens if we use a group 15 element? And this includes things such as, for example, we could have a phosphorus dopant or an arsenic dopant. So in this case, we have our lattice again with silicon atoms. This time, however, I'll mark this. So let's just say, for the sake of argument, that this was a boron atom, and let's make this one, for example, a phosphorus atom. In the group 15 element, we can form our 4 bonds, but remember, this is group 15. It has 5 valence electrons, so there's an extra electron out here, in addition to the regular 4, forming the lattice. Now this is just an extra electron. The importance, though, is that, like the hole, it's an extra charge carrier, and it has an energy level that is easier to get moving than promoting an electron all the way across the band. So there's more charge carriers available, it's more conductive once more, and we call this an N-type semiconductor. Now, this, at this point, may not seem particularly meaningful. All we've shown is that by adding these elements, we can increase the conductivity of our semiconductor at a given temperature, which is great, but the important thing about these is what happens when we use N-type and P-type semiconductors together, and that is going to be the object of the next lecture. So for now, just have an understanding of what doping the semiconductors and forming P-type or N-type semiconductors does to the charge carriers available in those semiconductors. And I'll just make a note, because we're introducing holes, in this case, for example, and electrons in this case, they become the most likely things to carry charge. They're called the primary charge carriers. And the same for these electrons. They're also that extra electron in N-type is the primary charge carrier of that doped semiconductor.